The physical framework of modern civilization relies almost entirely on a single material, steel. From the dense rebar grids buried deep inside concrete highways to the towering internal structures of skyscrapers, it serves as the irreplaceable, load-bearing skeleton of the human world. As developing economies rapidly urbanize, the hunger for this material surges. In nations like India, the drive to build new cities, bridges, and rail networks creates a staggering gap between the steel they currently produce and the millions of tons they desperately need to keep their growth alive. Meeting that demand presents a massive logistical hurdle. The century-old industrial methods of the past, which relied heavily on manual labor and small-scale forging, simply cannot produce the millions of tons required today. These methods are inadequate for modern requirements. To satisfy this modern appetite, industrial engineering has to be pushed to the absolute limits of physics and chemistry, operating at scales that are difficult to even comprehend. Building a nation's infrastructure today requires mastering two completely opposed methods of mass production. One harnesses chemical fire, the other wields man-made lightning. We begin with the first method, known as the primary route, which relies on integrated steel plants. These are the titans of the industry, operating with massive geographical footprints that can stretch across 4 to 8 square kilometers of land. The beating heart of these sprawling complexes is a vessel known as the basic oxygen furnace. The mechanism inside this furnace is extraordinarily violent. A water-cooled lance blasts 99.9% pure oxygen at supersonic speeds directly into a bath of liquid molten iron. In the main blow phase, the oxygen jet triggers highly exothermic reactions with impurities. This generates so much internal heat that no external power is needed. Solid scrap steel must even be charged first as a coolant, preventing the vessel from melting. Thanks to this self-sustaining chemical reaction, these primary giants achieve massive yields at blinding speeds, converting hundreds of tons of steel in under 60 minutes. But not all modern steel requires a massive liquid iron infrastructure. The secondary route, utilizing what are known as mini steel plants, skips the liquid iron phase entirely and focuses strictly on digesting solid steel scrap and sponge iron. This schematic shows the electric arc furnace. 3 massive solid graphite electrodes are lowered through the roof directly into the solid metal charge. High voltage current passes through them, striking arcs against the conducting scrap. The raw radiation rapidly melts the solid steel. We can see the brute force physics of this process expressed in this electrical requirements formula. The power consumed is directly dictated by the resistance of the steel itself. Overcoming that resistance requires roughly 350 kilowatt-hours of power to melt a single ton. Operating one of these units is a brutal sensory experience. The arcing process emits deafening noise levels reaching 139 decibels, and it draws such immense initial power that it causes local city grids to literally flicker. For cleaner, higher quality melts like stainless steel, plants will often substitute the arcing method with an electric induction furnace. This uses electromagnetic fields to heat the metal from the inside out, offering a much quieter alternative. Whether through arcing or induction, these electrical furnaces act as the agile recyclers of the industry, continuously transforming discarded scrap metal directly back into high-strength structural integrity on demand. The massive oxygen plants and the electrical recycling furnaces operate as a synchronized national ecosystem. Together, they provide the volume and flexibility required for rapid industrial growth. Take a look at this bar graph tracking India's crude steel production. You can clearly see a steep, uninterrupted climb between 2005 and 2010. Pulling a developing nation into the future requires exactly this kind of unrelenting velocity in structural output. This data table reveals how that massive volume is achieved through a strict industrial division of labor. Just 13 highly centralized primary plants handle the massive liquid oxygen operations. Beneath them, over 1,000 smaller, decentralized electric and induction units recycle solid scrap nationwide. This specific distribution is dictated by deliberate national policy, outlining exact capacity ratios for the future. The national blueprint maps this out perfectly. Government strategy targets 60% of all new steel capacity to be built out through the massive blast furnace route. while assigning exactly 33% of the load to the secondary electric and induction route. The towering skylines and mega infrastructures of tomorrow rise from a meticulously balanced equation. They are the physical result of mastering chemical oxidation and electrical resistance in tandem.